Hi, so welcome back. We're done with chapter 27, so we understand a bit more current and voltages and potential and resistance. Now we're going to solve circuits. By solving a circuit, I mean we're going to find a way to find the currents everywhere in a circuit. We'll focus now in this chapter on direct current circuits. What we mean by that is that it's a circuit when you have sources of voltages, batteries, that apply a constant voltage in time. The voltage doesn't vary in time. Later, we'll do different type of circuits where the voltage applied will vary in time following a sine wave, usually. Okay, so we have batteries that apply constant voltage. Note that this is a question of terminology. We often call the voltage applied by a battery, which the constant is also called an EMF. That stands for electromotive force. That's a very, very misleading term because what we call an EMF is actually a voltage in volts. It's not a force. So even though we call that an electromotive force, an EMF, there's a word force there. It's just unfortunate that is for historical reason that's what is used, but it doesn't represent a force. It represents a voltage. So the EMF of a battery is the voltage applied by the battery, simply. Okay, now we're going to do circuits which will get increasingly complicated. For now, we start with very simple circuits. If you have a circuit that contains, just a comment, if you have a circuit that contains only one battery, and there could be several resistors connected in any way you want. If there's only one battery, then the current always flows out of the positive terminal of the battery if there's only one battery. But with very shortly, we'll have circuits where you have several batteries, or we have things that are different than batteries and resistors. For example, we'll have things called capacitors. So in more complicated circuits, when you have several batteries, for example, it might happen that in some of the batteries, the current actually flows into the positive terminal. That happens. But if you have only one battery, then it's clear cut. The current always flows out of the positive terminal. If you have several batteries, it's not always true. So we'll see how to figure out the correct directions. Just a quick reminder, uh, what really matters to calculate anything physical for any physical application is always a difference of potential between 2 points. The actual value of the potential at any point in a circuit is totally arbitrary. If you want, you can take a very simple circuit in your lab and say, I'm going to decide to say that this point in my circuit is at 1,000,000 volts. There's nothing wrong with that. It's a choice, it's a convention. But what matters is really the difference of potential between 2 points in a circuit. So it doesn't matter if you have a point of your circuit at 1,000,000 volts and another point at 1,012 volts, or if you have a point at 0 volt and the other point at 12 volts. The only thing that matters really in physics is the difference of potential between 2 points, which is what we call the voltage. For example, if you have power lines at very high voltages, let's say 70,000 volts, 70 kilovolts, you have 70,000 volts in a power line. What we really mean by that is the following. Um, we really say that the line is at 70,000 volts above the potential of the ground level. So if you have a bird standing on the power line with the two legs touching the wire, even if we say the wire is at 70,000 volts, it makes no difference for the bird. The bird is totally safe because between the two legs of the bird, the delta V is zero because the two legs are the same electric potential. So delta V is zero, therefore it's safe. There's no current push into the bird because delta V is zero. But if you're touching this wire and with one hand and your feet are touching, let's say, the ground, you're standing on the ground and you're touching this wire there, then there's a delta V of 70,000 volts applied between one of your hands and one foot or your feet. So there's a delta V of 70,000 volts applied to your body. Then you're in trouble. And what happens, you have a large voltage across your body, and your body acts like a resistor, but if the voltage is large enough, you're going to have a current flowing through your body. And really what's dangerous is the current, the flow of charges through your body, especially if it travels to the heart. So if the flow of charges flows through your heart, then it's very, very dangerous and possibly deadly. But if, let's say, you're hanging from a wire at a high potential, you're just hanging like that in the air, your feet are not touching anything, you're just in the air, then you're still safe. But as soon as you establish a connection between 2 points at a with a very large delta V between the 2 points, then you're in danger. Okay, let me just introduce very quickly a few definitions and principles we work with. Well, we've seen most of that already. What we call a junction or a node is a point where two or more wires meet. Okay, and in general, there's an exception to that rule. I'll come back to that later. But usually, when you reach a point where there's a node, a current will split. Now, just a quick question. How many nodes are there in this circuit? Okay, you can pause the presentation and tell how many nodes and identify them. Okay, so there are 4 of them. There's a node here at point B. There's a node here, which is not labeled anything. There's a node at point F here, and a node at point D. So there are 4 nodes. Those are points where the currents will split. By the way, some people say that point A is a node. I don't know why. Maybe just because they see a wire changing direction here, bending. But this is not a node because the current cannot split here. The current that goes here must go that way here. So A and C are not nodes. Okay. Okay. Principle that we've mentioned in class, very important. The sum of the currents that enter any node must be equal to the sum of the currents exiting that node. Sorry about the typo there. So the net current coming in, the sum of the currents coming in equal to the sum of the currents coming out. This follows from 2 things. First, charges are conserved. You don't create or destroy charges. So if every second there's 2 coulombs entering a node, those 2 coulombs cannot disappear. They have to go somewhere. The other principle is that charges don't accumulate at any point of a circuit. So you don't have a piling up of charges at one point. So that means that at the junction, if 2 coulombs enter every second, 2 coulombs must leave that node every second. For example, let's say you have a node here, clearly here this is a node, and you're told that here in this wire here, there's a current of 3 amps going this way, and there's a current of 5 amps going this way. Then you know right away that the sum of the current coming in must be equal to the sum of the currents coming out. You know there's 3 amps coming out, so you must, there's 8 amps coming out, 3 plus 5. So there must be 8 amps coming in, and the only way it can come in is from this side here. So you know the current here is flowing in that direction, and it's equal to 8 amps. Okay. Okay, concept of branch. A branch is a section of a circuit that connects 2 nodes. So you go from one node to another node, that's a branch. Why do we introduce that? Okay, so again, a branch always starts at a node and ends at a node. Okay. What's special about the branch is that because it starts at one node and goes to the next node, the current must be the same throughout the branch. So the number of different currents there is in a circuit, which later will be the number of variables we work with, is equal to the number of branches. Because for each branch, there's one current. So number of branches equal to number of currents, different currents in the circuit. Okay, in this circuit, so we saw that there are 4 junctions. How many branches are there? Okay, so you can pause here and count the number of branches. Okay, so how many branches did you count? Well, you always start at a node and you end at a node. So there's one branch here. That's one branch. There's a second one here from there to there. There's a third one here from there to there. A fourth here from all the way to here. And a fifth one here. And finally, a sixth one from F to D. So there's a total of 6 different branches in this circuit. And each of these branches will have a different current. Okay? Here, how many branches? Well, how many junctions and how many branches? I leave that as an exercise. Well, okay, you can pause here and count how many junctions. So how many are there and where are they? Okay, so if you look at the, well, okay, if you look at the node, the junction, how many junctions are there? Okay, there's one here, there's one here, one here. So we are 3, 4, 5. There are 5 junctions in this circuit. How many branches? Okay, try to answer that first by yourself. Okay, so how many branches? Okay, that's one here, 2, 3, 4 here, 5, 6, 7, 8. So there are 8 different branches in this circuit. That means there are 8 different currents in this circuit. Okay? Okay, now we know the number of branches, number of junctions, and so on. And then in this problem, usually when we do a problem, usually we don't have the currents anywhere. But here they gave us partial information. So we're told here there's a current of 3 amps flowing here, that way. There's a current of 5 amps going this way, 10 amps going that way. So we know the current here, we know the current here, and the direction, the value of the current and direction of the current here, and we also know the current here. So there are 8 different currents in the circuit, but we're given 4 of them. Now we can use the rule, what we call the junction rule, the sum of the currents that come in equal to the sum of the currents coming out, to find the currents everywhere else in the circuit. For example, well, if I try this junction here, the sum of the currents that come in equal to the sum of the currents coming out. I know there's a 3 amps coming here, but I know nothing about this one or this one. So I have 2 unknowns here, and I cannot tell anything from that junction. So let's forget about that junction for now. Let's focus on, let's say, this one. Okay, so there's 10 amps flowing this way, so I know here there's 10 amps coming in here, right? Because it's the same current as, it's the same branch as at the top here. So this is 10 amps flowing here. So here, I know there's 5 amps coming out here, 3 amps coming out. So there's 8 amps coming out from those 2 wires. There's 10 amps coming in. So 10 amps come in, 8 amps come out. So there must be another 2 amps coming out. So there must be a 2 amp flowing this way. So that's it. We found the current in this branch here to be 2 amps flowing up. Okay, now we can go to this junction here. I know there's a 2 amps flowing into that junction. There's a 10 amps flowing out. Wait, so there's 10 amps flowing out, only 2 amps flowing in. There must be another 8 amps flowing in, and that must come from this side. So I know from this branch here, there's a current of 8 amps. Okay, that way you can always double check after that. That way, if you look at this junction, there's 8 amps coming in, 2 amps coming in, so a total of 10 amps coming in and 10 amps coming out. So we found the current here. Now I can go here. From this wire here, I know there's 6 amps that flow in, 6 comes in, 8 comes out. So if 6 comes in, 8 comes out, I must have another 2 amps coming in. So I must have a 2 amps flowing that way here. And again, I can double check after that my answer is correct. If I look at this junction here, there's 6 amps coming from the left, 2 from the below. So 8 amps come in, 8 amps come out, everything works out. Then I can go here, that junction. I know here from the left there is a 5 amps here that was coming from the left, 6 amps comes out. So if 5 amps come in, 6 amps come out, I'm missing 1 amp coming in. So there must be a 1 amp coming in. And so I know there's a 1 amp current flowing in that branch. Now, by the way, I can go back here and look at that junction and make sure that everything is consistent. I have a 3 amps coming in, 2 amps come out, and 1 amp come out. So 3 amps come in, 3 amps come out, everything works out. So that's it. We've solved the circuit, we found the currents everywhere. Notice in that question, it's a bit different than usual questions. We were given some of the currents, but we're not given the voltages of those 2 batteries. They call that E1 for EMF1 and E2 for EMF2. Those are unknowns. Actually, from what we are told here, we could later we'll work out the voltages of those batteries. But for now, we found the currents everywhere in the circuit just using conservation of charges at the nodes. Okay, next time we're going to pursue that and solve more complicated circuits. Thank you.